Hey to you. Happy birthday to you. Happy birthday, dear Mark. Happy birthday to you. Yeah. Make it.
I think the microbes did it. From Microbe TV, this is Matters Microbial, a podcast about the wonders of microbiology, microbiologists, and microbial centrism. This episode was recorded live at ASM Microbe in Atlanta, Georgia on June 16th, 2024. Welcome, Micronauts, here in Atlanta. Welcome to this live podcast session at ASM Microbe in Atlanta, Georgia, of all places. And I'm your host, Dr. Mark Martin, Associate Professor of Biology at the University of Puget Sound in Tacoma, Washington. Today is the 45th episode of Matters Microbial. Also, June 16th is Father's Day, the anniversary of my late parents' wedding, and my own birthday, as you saw. Those of you who watch and or listen to the podcast and spread the good microbial word to others, thank you so very, very much. One of the major problems that physicians and patients have in hospital is decreasing the chance of transmitting disease-causing microbes. You'll notice I don't use the word pathogen out of deference to Arturo Casadevall. For many years, it's been found that some metals appear to have antimicrobial effects, and I have certainly demonstrated this oligodynamic effect to my various micronauts in my microbiology courses over the years. But during the recent pandemic, I read a great deal about trying to use metal surfaces to decrease the chances of transmitting disease causing bacteria and viruses. I knew about silver, but copper? So it's thus a real pleasure to introduce a friend and colleague, Dr. Michael Schmidt of the Medical University of South Carolina, to our Quality Quorum to discuss his own work in this area. Now, I should also say that I've been a guest from time to time on This Week in Microbiology, where Dr. Schmidt is co-host, so I wear a pin that reads TWIM adjacent. So we made Michael a Matters Microbial adjacent pin. Welcome to our live Quality Quorum today, Michael.
Thank you, Dr. Martin. It's a pleasure to be Microbial Matters adjacent. It's a great time always listening to you on Microbial Matters, and this is a shameless plug for his podcast. If you haven't listened to it, it's only got 44 past episodes, so you can technically catch up. So it's really a fascinating podcast that he interviews people like you and asks them all things microbial.
I've actually gotten some really good leads on people to have in August on the podcast from here, so I'm really excited about that. Michael, can we begin with give a little bit, and I don't know where this expression thumbnail sketch comes from exactly, but a little thumbnail sketch of your path that takes you to where you are now, microbiologically speaking.
Okay, I grew up in Chicago. I'm a frustrated Cubs fan. It took them until this century to win a World Series. I went to Chicago high schools. I went to Chicago public schools. And then I went to the University of Illinois in Chicago, that we affectionately referred to as Harvard at Halstead. And there I did undergraduate research on, of all things, cave spiders. And it was really cool. I got to go to some really neat caves, especially the big cave in the United States, Mammoth Cave, where I learned how to get myself out of caves, and which is effectively how I became a microbiologist. When I was an undergrad working in the lab, the TA who actually helped with the microbiology lab was in the cave spider lab. And she had gone to graduate school at Indiana, and she then encouraged me to pursue an advanced degree in microbiology at Indiana based on my experiences in the undergraduate microlab. I found microbes to be fascinating. So then I went to IU, where I interacted with a cast of characters and stars. Everyone from folks you may know, Norm Pace, Howard Guest. My mentor was Walt Konecka, who happens to be a Karski winner, just like our host, Mark Martin. He happened to be the second recipient of the Theodore Karski Award for Excellence in Undergraduate Education. After graduate school, I did a postdoc in Stony Brook, New York, in the laboratory of Don Oliver, where I worked on bacterial protein export, and then I went to my current position where I've remained for the last 35 years at the Medical University of South Carolina, where I've had to do a little bit of everything.
Which brings us to this real issue. You'll discover when you learn a little bit about Dr. Schmidt, he does a lot of work teaching dental students, but he also does a lot of interesting research. And one of the things that struck me is when we originally came up with this idea of this topic, how much Michael had done in it. So talk to us about the genesis of like taking a penny and making a cure out of it.
That is really cute. Very, very cool. It all starts with the president of our university who gets a phone call from a group, a trade association, very similar in form and function to the American Society for Microbiology, except this was the Copper Development Association. They received a large federal grant, and federal grants have requirements that you hire credible people to conduct the science that they got the money for. So President phones me up. I happened to be working for him at the time. I was the director of Office of Special Programs. And Ray Greenberg said to me, talk to these folks, see if our institution can help them. So I phoned up their head of R&D, an individual by the name of Harold Michaels, who's got a PhD in engineering, and talked to Harold, and we had an audition. And so I assembled an interdisciplinary team of infectious disease physicians, infection preventionists, as well as engineers, where we principally asked one simple question. Could placing antimicrobial copper surfaces on key touch points in the clinical environment reduce healthcare-associated infections? For those of you who don't know, healthcare-associated infections truly cost everyone in the United States approximately $147 billion. 147 B with a billion dollars. And that's because we don't actually know who's actually paying the tab. Some of it's paid for by your insurance carrier, some of it's paid by the feds, some of it is absorbed by the hospital system, and so it's a big problem. It's in between the revenue stream of Ford and GM. I mean, we're talking big bucks. Now, to give you a benchmark, cybercrime costs the country approximately $500 billion a year. So we're talking big money, and my little experiments of asking, could I strategically place metallic surfaces on the surface, would it change healthcare infections? And so the bottom line up front, yes. We dropped the healthcare-associated infections associated with 3 independent ICUs at major medical centers. My institution happened to be one, the Ralph H. Johnson's Veterans Medical Center another, and then Memorial Sloan Kettering in New York City. And we dropped the collective infection rate in those ICUs by 58%, comparing and contrasting patients in beds without copper and patients in rooms and beds with copper.
So it's interesting. I think that most everyone here has heard, for example, that silver is antimicrobial. And back during the dark ages of my life, I would have students look at how they would put a little bit of silver wire on a petri dish that's been spread with bacteria, and you would see a zone of clearing. Ditto with copper. And that's a long ways from what we're hearing about here. Do you have some thoughts about the mechanisms by which copper can inactivate bacteria and viruses?
It's theft. It's pure and simple theft. The metallic surface effectively is stealing the electrons from the bacterial membrane. And everyone in this audience knows that in order for a bacterium, regardless if it's an aerobe or anaerobe, has to put an electron into the membrane. And when that electron goes in, what goes out with it as well? A proton. And so what happens is the electron goes into the metal. And it's the same reason we use copper for the wires for our electricity is you get flow. So you have fluence. And fluence is the magic word because it's the flow of the electrons. So when that poor proton is waiting for its mate to go back through that ATPase to make energy for the microbial cell, it's all about proton gradients, folks. I mean, you can go back to the books and look at the new physiology textbook, and there that equation is. You know, the proton gradient potential is dependent upon delta psi and delta pH. It's all about the pH. And so what happens inside the bacterial cytoplasm is the pH goes up big time. So let me ask you guys a question. How many free protons are inside a bacterial cell? You know the volume of a bacterial cell, right? 10 to the minus 15 liters, correct? Good enough?
Everyone knows that.
Yeah. I mean, it's in the New England Biolabs catalog in the back.
That means it's true.
You can find out. The other thing to appreciate, how many of you here know Avogadro's number? 6.023 times 10 to the 23rd. What pH is the chemistry of life? It's about 7.4. What is pH? The concentration of protons. It's protons. And so when you figure out, and it's a mole number, not a mole number, excuse me, Dr. Quinn, it's a logarithmic number. It's 7.4, and you take the log to the base 10 is 7.4, and you can figure out the mole number. But on average, the average bacterium has at any moment in time between 25 and 80 protons. Yet the mere act of rotating a flagellum consumes many, many millions of protons. So how much does energy consume? So it's literally shuffling protons back and forth across that membrane, and that's how it makes energy. But if you have no electron because that damn copper metal has stolen it, you're in trouble. Now, all of this has been elegantly demonstrated, the mechanism, by other folks, not me. This is work principally of Bill Keevil at the University of Southampton, and he has published some really elegant studies using redox dyes. And the redox dyes can actually show you that when you put the bacterium next to the membrane, the lights get turned off. Because the redox dyes are all dependent upon whether or not you are flowing electrons. And what typically happens is the bacterial membrane is de-energized. It collapses. That potential is gone. Now, with no potential left, you're in a protonic deficit. Those electrons that you're using to make energy have to go somewhere. And where do they go? They go to the nucleic acid, they go to the proteins, they go to the membrane, and we're done. We poke holes in things, and we're done.
Have you ever noticed how many things are due to holes being poked in membranes in microbiology? It's bad enough what we call them, perforins and things of that nature, but it's everywhere. Now that's for bacteria. What about viruses? Viruses are apparently inactivated by copper too.
Oh yeah. Copper metals can, and the reason I say metals is because there are alloys out there where you can effectively make brass, you can make, beautiful things that don't tarnish because copper will change colors. And unlike silver, copper is active regardless of how tarnished it is. Unlike silver, when it tarnishes or it passivates, to use the metallurgical term, it becomes passive. It's no longer active.
I'm learning so many new words today.
Oh, you have to hang around engineers. They will blow your mind. But then remember the little bit about how many protons in a bacterial cell? You can literally kill a chemical engineer with that factoid. I mean, they're amazed. But what happens is with the virus is they don't actually know the precise mechanism, but they think it destabilizes the membrane if it happens to be a membrane-based virus, or the capsid if it happens to be an icosahedral type virus. And it can kill, literally inactivate norovirus.
So we can take the song, It's All About the Bass, and we can change it to It's All About pH, couldn't we?
Yep.
You'll be performing it later, I know, Michael.
No. Happy Birthday is my repertoire.
So this is interesting. Now we have this type of metal that on contact appears to have a deleterious effect both on bacteria and on viruses, and it's not specific in a particular fashion. It makes me think, by the way, of copper pitchers that I often see in Indian restaurants, whether they act, and I'm thinking that's a great project for students of mine to think about. Does that really reduce the number of CFUs per mil? I haven't tried that.
Well, the answer to your question is yes. The folks who discovered the antimicrobial properties of copper, this observation is literally 8,000 years old. And you know who discovered it? Women. Women discovered this, not men, women, because they were assigned to go to the stream or the well head or the river and get the water for their family. And you don't need an MD to diagnose diarrhea. Everybody's had it. Everybody knows it when they see it. And what the women appreciated some 8,000 years ago is when they carried the water back to their residence in copper vessels, their family had less diarrheal episodes. But they had to let the water sit in order to inactivate to a potable concentration. Now, today we have many more efficient ways of inactivating microorganisms, and the women knew to collect water upstream from where their effluent went in. So that, again, the women effectively were much more clever than the men.
Absolutely. And this actually, there's always a little grain of truth in other ways of knowing, and that always fascinates me how they echo up to today. And it reminds me of times I would talk to my parents about something a scientist had discovered. My mother would go, well, that's pretty obvious. And I'd say, well, not to a lot of people, Mom. And so that's the situation we're talking about here. Real things seen by real people still with us. Reminds me of Rita Caldwell's issue filtering water through sari cloth to reduce the incidence of cholera. Wonderful solutions to problems.
And again, Rita taught women how to manspread, to sit, and she had the sari cloth across their lap and pour the water through.
I'm holding back comments for Michael, but you'll be glad I did. So he's a piece of work, is my friend Michael. But what I was going to say is, and I just want to remind everybody that I like to put links to things in the show notes for this podcast. So many different articles. This gentleman sent me, I can't tell you how many links. They're all going to be there when this episode goes live. So I really urge you to look at it, because this is a topic that you can use educationally with anyone. And it's really worth our while. Most of the time when I talk about microbes with people who aren't my Quality Quorum, their eyes slowly go back into their heads. I'm well aware of that. But this is something that everyone can kind of catch up with and think about. And it's a good way to teach, I think. So this is wonderful, Michael.
So let me ask the audience a question. If one jumbo jet crashed each day, every day, for the foreseeable future, would any of you get on a plane today? No. This is precisely the number of people who die each day, every day in the United States from healthcare-associated infections. One jumbo jet's worth. That's the call to action. Why we need to ensure that we wash our hands, we effectively sanitize our healthcare institutions subsequent to patient discharge. We don't scrimp on anything. The copper that we were introducing into the environment was an add-on to the existing standard of care. Sloan Kettering, my institution, the Medical University of South Carolina, and the VA are all serious about infection control and disinfecting their rooms afterwards. And so we did a pragmatic clinical trial. So I'm using a fancy word. That means you just took whatever you got. If they introduced a new cleaning protocol, it got added. You had no vote in the matter. This wasn't a pure study where any patient could come into the room. Unfortunately, we had a number of individuals who couldn't fit into a standard hospital bed. So their hospital bed with copper rails was taken out of the room because they had to use a bariatric bed. And so that dose, because it's a dose-dependent study, that dose was removed. Riddle me this. Did it change the rate of infection drop? You betcha. Because you remove the active agent. The beauty of copper is it's continuously active. It's working 24/7 independent of the cleaning crew, but the cleaning crew still has to show up. They still have to do their job every day. They still have to take out the trash, mop the floors, do everything that our friends at the CDC say must be done in order to maintain our infection rate. Even though we're losing a jumbo jet worth of folk each day in the US, other nations, developed countries, are losing far more.
That's true. And we tend to forget all that. And you know, we're so focused on our own situation economically and socially. And this is a worldwide issue. And this is one of those solutions that is transmissible to a bunch of different cultures. I shouldn't use the word transmissible, I know, but you know what I'm getting at. It's translatable to a bunch of different situations. Now, there is a microbial elephant in the room. We all know about the rise of antibiotic resistance among many microbes. Talk to me about the possibility of metal resistance by potential pathogens.
Well, we all know, we've read the papers that microbes, if you give them ionic copper, Cu+, Cu++, they enhance their ability to pump things out. And you can add concentrations, but the metallic opportunity is an infinite sink, because you can drop a penny in water and it'll still be there tomorrow, it'll still be there next week, it'll still be there the following week. Not all of it is going to be there. A little bit is going to float away, and that's effectively what happens. We're doing this antimicrobial activity in air. I mean, the microbes get deposited, and there's the ick effect. You know, if you happen to sneeze or vomit, we affectionately refer to these things as fugitive emissions. You know, if a patient so happened to have...
That's a band name.
Fugitive emissions?
Yes. Sorry, Michael, but it is.
Is it really?
No.
Oh.
That was for you, Jenny. Anyway, this is wonderful, and I wanted to say parenthetically, I wasn't trying to be silly about this. We're so used to the idea of resistance to different agents, and in my mind, I'm thinking things like, I know that there are efflux pumps that pump out metal ions very effectively, but you see the difference here is this is the infinite sink of metal. So in order to do a similar experiment like we're used to doing on Petri dishes, we would have to have a piece of metal, put a droplet of microbes on them, make sure that that was of uniform depth so that the microbes within that drop are being exposed to the same thing. And this is something that had not occurred to me until I read all of the papers and such that you sent me.
Well, it's referred to as the dead body effect. The US EPA is the one who governs whether or not you can say something is antimicrobial or not. And I've been very careful to refer to it as antimicrobial copper. I'm not a shill for the copper industry. I happen to be making certain that I message things according to what the US EPA requires. And what the US EPA required is you kill something and then you put more bacteria on top, you kill them, and you keep stacking and packing, asking the question, how many layers of bacteria have to, the dead bodies, have to be there before it no longer works? Well, you can stack and pack quite a few before its activity drops, but the activity is still omnipresent. And so if the cleaning crew is doing their job, not doing the licking and the promise like my mother would say, and does their job properly, and this is one of the things, so those of you going on to healthcare, when you are looking at the contract for cleaning, make certain it's performance-based where you actually know how clean that room is. Because some rooms are different shapes that takes longer to clean, and you just can't say you got to get every room done in 10 minutes and every room done in 5 minutes. The room has to be clean to a standard, and there are defined standards. It's typically that if I go in with swabs or Mark goes in with swabs, that the colony forming units be no greater than 500 per 100 centimeters squared.
That's not much.
No. But your risk of acquiring an infection, if you randomly sample and it's greater than about 250, there's literature, not done by me, done by infection specialists, folks like Stephanie Dancer and others, that in the literature, the number is about 2.5 per centimeters squared. There, your risk increases. And your risk is a function of you, how immune compromised you are, what you're in the hospital for. All of these variables come into play because we know not all infections are created equally.
Now, this is very interesting. And one thing I wanted to bring up is that when I am trying to, don't take this the wrong way, folks, teach students about making antibiotic-resistant bacteria by spontaneous mutations, so you get the colonies on plates. It's good to show them that. If I have too many bacteria on the plate, it doesn't work very well. That's very similar to your dead bodies idea.
Yeah.
So this is very interesting, even when you're talking about it, not geographically, but geometrically with the layers on top. So can we, since we know it works, we know how to do this, so we've done a certain number of studies. Has there been any movement to regularizing this to all hospitals now?
It's interesting. It's how stuff gets paid for. And principally, changing out the furniture in the room is a capital expenditure.
Yeah.
Now, those of you who have gone and gotten your MBAs know that you purchase revenue-generating equipment as opposed to revenue-sparing equipment, correct? So in our study, and the Center for Medicare Services published a model. It only lived on their site for about 4 weeks. So I put my data into the model. It took me $69,000 to outfit 20 rooms. And so if I put that money in, and for 1 year, I would generate $6 million in savings from healthcare associated infections. And the economic model is pretty straightforward. It was not my model. It was CMS's model based on my zip code, based on my hospital's performance data, all of the variables. And so you can invest $69K and save $6 million. Now, you think the leadership team would say, hey, that's great. We're going to save $6 million. But that's not generating $6 million. It's saving. And that's fundamentally the hazard we have with how we pay for healthcare. Everybody pays. No one's writing the check for the $6 million that I saved. And so therein lies the rub. Now, nation states who have public funding of healthcare appreciate this. And so I got summoned by Her Majesty the Queen's government. And so we went over and briefed the folks in Great Britain. And, you know, they give you a courtesy call. And this was through the auspices of Bill Keevil, who was trying to start a similar clinical trial in Great Britain at the time. So we met with Wales, Scotland, Northern Ireland, Great Britain to talk to them. They gave us an appointment for 30 minutes. We were there for 5 hours.
That's encouraging. What I like about this approach is it's something that's transferable. It's something that is, when I use the word low tech, I don't mean that mining copper and smelting it and manufacturing it is easy. What I mean is a lot better than machines that go ping, according to Monty Python, if those of you are old enough to remember Monty Python. And that's what we have, is a situation we have so much stuff that's machine-based, and this is not. And this does work, and I love the idea of it. I wonder if there's going to be a huge number of barriers to getting this in more forthright places.
It's an issue of understanding. It's not so much money. It's really fabrication.
Okay.
We fell in love with injected molded plastics. We love them. Except the only thing that is loved more by us than injected molded plastics is the bacteria and the fungi love injected molded plastic. And in fact, your good scourge friend, Candida aureus, literally makes barnacle-like cement where it literally attaches, and you sort of need a thermonuclear device to get rid of it out of your hospital. And there's been some posters on that around here. But we haven't ever tested it on Candida aureus to see whether copper will actually, take it out. But we've learned how to put copper into injected molded plastics. It works. It's a concentration function. You have to make certain everything is properly grounded, and you have to go through safety trials. It's not as simple as putting foil on rails.
Well, I like the idea of this, and what I want to do today is we have about 12 minutes left, and what I'd like to do is have a summing up by Michael. I'm going to ask him questions about his background a little bit and what really got him most interested in microbiology, and then maybe take some questions for all of you, because this was kind of new to me, the idea of metallic copper itself. So do you have any words of advice about getting the word out about this approach, or any hopeful things to share with people? We know it works. We know it saves lives. We know it saves money.
So we've all bought coffee at this meeting, right? About $6. If you had a loved one in a hospital bed, would you give them $6 to put copper into the room? That's principally the cost, $6. Most family members would do that, and it's all about hospital stay. The average stay in a U.S. hospital bed is about between 4 and 5 days. If you get an infection while you're hospitalized, you effectively, and this is an aggregate average from CMS, you end up staying 19.2 more days, and you don't have to be a healthcare economist to know that costs more money, right? And to the bill to the payers, and payers is plural, it's about 47K. God help you if you get an antibiotic-resistant infection, then the number goes up.
So everyone here is familiar with the idea of charismatic vertebrates. Porpoises and orca that everybody love. And we think about how much we like otters. They're very cute. And then there are charismatic invertebrates. In some ways, what works in medicine is under the same law of what's charismatic as well. So the idea of doing this that we've just heard about doesn't occur to people because it's not flashy?
No, it's old.
Yes. And smart.
It's old technology, and in fact, in the public houses that our founding fathers frequently, the bars were covered with metallic copper because they would eat. And they would eat off the bar. They would put the food down on the copper. They didn't get food poisoning. And, that was good.
There are some things I'm going to be trying back in the lab very shortly, I think. I bet I'm not the only one either. So, Michael, what I'm going to do right now, and I want to remind everybody at the conclusion of this podcast, there's some swag here, which you can come help yourself to. And we'll take some questions as well. But this is what I'm going to do now. I'm going to ask Michael, what is the one experience that made you a microbiological convert?
I think it's the first time I saw E. coli on EMB agar. That metallic sheen was wow. And then I had to understand how it made that brilliant green metallic sheen. And it was just remarkable. EMB agar is remarkable. And then you fast forward a few years and you discover chrome agar. Chrome agar is really wild stuff. And as you begin into the microbial world, you just, again, you have Mark's buttons. You go WTM.
What, the microbe?
What's going on here? Yeah. And I was really fortunate, and I went to graduate school that had really terrific microbial advocates. Yes. I mean, I literally learned the Z scheme of photosynthesis from the guy who figured it out, Howard Guest. And it was really wild. My mentor, Walt Konecka, taught the first class in molecular biology at IU in 1960. They were still having arguments at this meeting whether or not DNA was real. I'm serious. Even after the Watson-Crickery in 1960, there was the jury was still out. And folks like David White taught me the wonders of Myxococcus xanthus, Stigmatella aurantiaca, and gliding motility. And we can't forget Art Koch. Any of you who have ever tried to figure out how to make a square bacterium, and remember, square bacteria divide via binary fusion. So how does a square become a square via binary fusion? Discuss. We have a mathematician in the room, so she's going to be busily doing the calculus.
So this is the kind of thing that changes lives. And I often talk about the fact that you want to face this overwhelming microbial greatness. That's what you want to transmit to your colleagues, to your students, to the people at home that you know. That's one of the goals of this podcast, in fact. So before we have an outro and all the rest, I think it's important to see if there's any questions for Dr. Schmidt from the audience.
Oh, you can ask Dr. Martin questions as well. Yes, sir, in the back.
So copper itself is going to be a finite resource on our planet. And if we're going to start implementing copper in the hospital, we're going to be competing with housing, with industries. How available is copper to compensate for these matters?
That's a really good question. And the chief sustainability officer of a very large health system asked me that very question. And I challenged that individual with the following: how much of the hydrocarbon your facility consumed is still in use? 80% of the copper that has come out of Mother Earth since the Bronze Age is still in use. Can you say that about hydrocarbons? So it is a finite use, and we have to do it strategically. You have to put it where the risk is greatest. You don't coat the facility with copper. What you do is you put it where the objects that the patient is most frequently encountering, because 80% of the infectious diseases transmitted in the hospital to the patient are a consequence of touch. So the bed rail is why we went to the bed. We didn't do anything about the footrest, because how often does the patient play with the footrest? We didn't do anything with the headboard. We did it with the rails, because in all hospitals, what is paramount is the safety of the patient doesn't fall out of bed. We do this with our kids. We wall them in the big boy and big girl bed with pillows so they don't fall out. Every person in healthcare is taught you never turn your back on the patient without the rail being up. And so the rail is it. Another question. Yes, sir.
I thank you both for this very informative discussion. A quick question for Dr. Schmidt. So you already described the antibacterial, antiviral mechanism of copper. I wonder if this is similar to silver, and if you compare them under same condition, who wins? Efficiency and
that study wasn't done by me. It was done. Bill Keevil at the University of Southampton and Harold Michaels have studied the effectiveness of copper as well as silver, and copper wins every single time. Silver passivates, and when it's in atmospheric concentrations of oxygen, it tarnishes. Any kid who's ever polished the family silver before Thanksgiving knows. And once it passivates, it's no longer active. It no longer is able to steal electrons because it's built up this passive layer so that the electrical charge cannot flow. Gold, on the other hand, is noble. And it's not all that great from an antimicrobial perspective, but it still transfers current really well. So it's when the microbe is interacting with the metallic surface, you get some copper ions being liberated by the inherent metabolic activity of the copper. It's actually copper ions that are released in situ in close proximity to the bacterium. And so, but you have so many coming across, you can't make enough pumps fast enough. Silver effectively is interacting with the sulfhydryl groups in the membrane and the outer membrane of the gram-negatives and the mycobacteria in order to inactivate them.
So I'd like to take this opportunity to thank Dr. Schmidt for this, and I can do something I normally can't do, which lead a round of applause.
No. Well, I'm here today because my other podcast co-host couldn't attend Microbe this year, so I dragooned the ever-adjacent TWIM individual, Mark Martin, and so turnabout fair play, he said, well, if I'm coming on TWIM, then you have to come on Microbial Matters. And Mark, it's been a pleasure interacting with you here today on the ASM booth. And let's do it again.
It's been a lot of fun. This has been Matters Microbial, a weekly podcast about the wonders of our microbial world and the people who study it. You can send questions, suggestions, or comments to me at mattersmicrobial@gmail.com. Show notes from today's episode with tasty links can be found at microbe.tv/mm. If you like our work, please consider supporting us at microbe.tv/contribute. I'm Doc Martin, and you can find me in the biology department of the University of Puget Sound in Tacoma, Washington. Dr. Michael Schmidt is at the Medical University of South Carolina. Many thanks to Ray Ortega for organizing all of this, and of course, Reber Clark for the wonderfully quirky music. I hope that you've enjoyed being part of our Quality Quorum today live. See you next time on Matters Microbial.